I'm Professor Kircher again for the recording's sake here, but this is ME 597, which is actually an ad hoc class, which basically means it's not a permanent addition to the schedule of classes yet. I just created this class last semester, and this is my second time, sorry, last spring, and this is my second time teaching the class. So there were definitely some kinks last semester, and we've ironed a lot of those out, but I would expect some kinks this semester as well. In particular, I'm learning kind of what the best format is to support both in-person and online learning for this class. Eventually I would love to make this into like a large course that people can take beyond Purdue, so an open online class. We're not quite there yet, I think, with all the kind of mechanisms and stuff like that for the class, but hopefully you guys can provide feedback that'll get us a little bit closer to that goal. So today we're going to be talking about basically what is the title of this course, Distributed Energy Resources. What does that mean? Why might we want to study that? I think some of you are maybe already working on these topics in your research, but others maybe just be interested and want to move in that direction. And then we'll talk kind of, that'll be roughly the first maybe half to 3/4 of the lecture. And then the remaining portion, we'll talk about what we're going to do in this class, what's the structure, and what are some of the policies, again, for in-person, for online, what do the exams and the projects look like. By the way, if anybody has questions, please just go ahead and if you're in the room, raise your hand. If you're on Zoom, I think the easiest way is probably for you just to unmute and speak up. Because I don't have a lot of visual cues right now about what's happening online in the chat and with hand raising and things like that. So just go ahead, don't be shy and speak up. And then I always like to say in classes like this that if you have a question or if something seems a little confusing to you, probably half a dozen people in the class have that exact same question. So please do, speak up, raise your hand, interrupt me. I would love that to be more of a kind of a conversation than a traditional lecture. And if you have that question, yeah, again, you're kind of doing a service to all your friends in the class who may have a similar question. So, okay, so diving in here, what are distributed energy resources? I'll give a few examples, but at least in my mind, DERs are electrical devices that plug in at the edge of the power grid. And I'll talk a little bit about what that means, but generally speaking, the power grid has huge machines, things that might be big enough to power whole cities, and it has gigantic, many mile long transmission lines, and then those feed into kind of the city scale or neighborhood scale distribution grids that you see when you walk around a town like West Lafayette. And then those sort of feed into the electrical wiring and outlets and things like that we have in buildings. So that's kind of the outer edge, really, is where we're focused within that larger energy system. And then the other adjective that I put in here is controllable. So and this is maybe contentious if you talk to other people who work in the area, they might give you slightly different definitions, but the vision in this class is that these are sort of smart devices that are maybe internet connected, that have some computing and communication capability that we can talk to and ask to do things, and they'll respond in interesting ways. And that's really what this class is about, is how to sort of understand and eventually control these devices. So here's a schematic of what kind of a traditional power grid of the 1900s looked like, and what much of the power grid still looks like today. So we can start on the left here at the generation station. So this could be, say, a nuclear power plant or a coal-fired power plant. It could be a hydroelectric power plant where you dam a body of water and essentially let the water fall through a turbine to generate electricity. It could also be wind turbines, solar panels, and other kind of alternative energy sources. These will typically, the power that output from these power station will go through a step-up transformer, which increases the voltage. So basically, stepping it up to somewhere in the range of 100 to maybe a couple hundred kilovolts. And that goes through a transmission system. These are the large overhead power lines that you might see like on the side of a highway if you're on a road trip. And the reason that we step up the voltage between the generation and basically the supply and the demand for electricity is that power losses over conductors, long conductors like power lines, are proportional to the square of the current that's flowing through the power line. And the power that's transmitted is the product of the current and the voltage. So if you do a little bit of math, you find that basically you can transmit with much lower power losses if you transmit at much higher voltages and therefore at much lower currents. So this is typically long distance, high voltage transmission. And then we would again go through a transformer and step back down to a lower and safer voltage for distribution within the neighborhoods that we live in. And so within the distribution system, that's the sort of green power lines that are depicted here. We might have larger customers, like a big factory, for example, where we would find maybe relatively high voltage, say in the 20 to 70 kilovolt range usage. And this would be used to power large machines on assembly lines and things of that nature. We might find, say, a building like the one that we're in here, a large office building or a classroom type building would have kind of roughly 10 kV service. And then in typical buildings like the ones that probably we all live in, we typically have either 120 volt or 200 volt, 240 volt power lines, power outlets. So this is for plugging in electronics or things like air conditioners, larger appliances in typical buildings. By the way, I should have said this at the beginning of class, but these slides are online. So if you would like to open them on your tablet and mark them up as we follow along through lecture, you're welcome to do that. Probably the simplest way, if anybody wants to do that right now, is just to Google Kircher Purdue, Kircher, my last name, and then my website will come up. You click or tap on the teaching, and then you'll find the slides for today under the DERs class. All right, so that's kind of what the power grid looks like. And so really DERs are things that plug in over here, kind of at the edge of the power grid. So I'll just give you a bunch of examples. And these are things that we will study in more detail over the coming couple of months as we take this class together. One is solar photovoltaics. Often these are on rooftops, but we also might see them out in a field somewhere. These basically convert the energy that's in sunlight into electricity. So here, there are some plots here of basically what the power output of a solar panel looks like under different conditions. So in the top right here, basically we have time. This is a 1 day span, and this is the power output. It's a little small, but on the vertical axis. And so you can see the orientation of the solar panel is going to determine significantly when it produces power and how much power it produces. So this would be a south-facing panel for us in the northern hemisphere, where the sun is in the southern part of the sky. And this would be more like a west-facing panel. So you can see that the panel that faces west is going to catch more afternoon sun. It's not going to be as intense. We won't see as much, but it'll shift kind of the peak power production to later in the afternoon, which you could imagine being useful if that's when people are actually using electricity. They get home from work and turn things on and begin cooking and so forth. Similar graph here, running roughly 1 day, and we have the power output on the y-axis. And here I'm showing seasonal variation. So this is the power output of a solar array that's on a rooftop and at a pretty steep angle. So actually this is the summer here. Actually, let's look at the blue curve, which is the winter output sort of at the end of the year in December. And you can see that the power actually between the 3 seasons, winter in blue, spring here is in green, and summer is in red. The power output is actually highest for this particular solar array in the middle of winter. And the reason for that is that the sun is low in the sky in winter. And so a steeply tilted solar array will be having basically a smaller angle in between the sun and the panel, and therefore more power production. In summer, however, we see a little bit of a lower peak, but a little bit of a broader curve here. So the area under the red curve might be similar to the area under the blue curve. And so we'll talk in this class a little bit about what is the optimal orientation for a solar array. Or if you have it oriented in a certain way, what can you expect from the power output of the array at different times? And then, of course, solar is highly sensitive to what's happening with weather, in particular with clouds. So here we have a sunny day profile for solar power output. So you can see it's got this kind of nice, clean bell curve shape. This is a cloudy day, so much less solar electricity generated, as you might expect. But either of these, you could imagine, are fairly predictable. They're not too variable. They're fairly smooth. And this is a partly cloudy day over here. So you can see that we're kind of flipping in between this, what's called the clear sky envelope, this kind of hill-shaped thing over here, and then the sort of fuzzy thing down here from overcast. So clouds move over the panels, and this changes very quickly the amount of power that they produce. And so we'll learn a little bit about basically how to map weather data into the power output of a solar panel. By the way, please do feel free to raise your hand if you have questions or comments on this. Yes?
For the different times, if there were a shallower panel, would we expect that to be kind of flipped for the December, June, and March?
Would we expect this to be flipped for a different panel angle? Yes, I think so. Right. So typical guidance for a solar array, the ideal solar array in the northern hemisphere is to point it south and then to tilt it at an angle that's equal to the latitude. So we're at, I think, about 40 or 42 degrees latitude. So we'd want to tilt it about like that. So for an array that's tilted more at that kind of optimal orientation, we probably would see that the clear sky envelope for summer, the red curve, would be above the blue curve here, or a similar height. Yeah. Does that make sense? Yeah. Cool. All right. So why do we care about solar panels in particular? Well, one reason might be that they're now extremely cost-effective ways of generating electricity. So what I'm plotting here, there are 4 different subplots, and they run from the year 2010 to 2020. And so that's time on the horizontal axis, and then the vertical axis is essentially the installed cost for a solar array, normalized or divided by the capacity of that array. So an array is just a bunch of solar panels together. So this is in units of dollars per watt. So a typical, say, residential solar array, something you'd find on a single family home, might be around 10 kilowatts, kind of order of magnitude. So here in 2010, that 10 kilowatt or 10,000 watt array, multiply it by the 7.5 here, we'd get about $75,000. Is that right? Yeah, that's right. So quite expensive back in 2010. However, in between 2010 and 2020, prices dropped by roughly 2/3 or more. And so here, that $75,000 array in 2020 would have cost only about $27,000. Still a lot, but a lot more affordable. And these cost declines have persisted in the last 5 years as well. So the different subplots here show different applications, basically, for residential solar. Yes, question.
Is it just for materials, or is it like what people have been charged actually, like with labor?
Yeah, so that's a good question. I'll repeat for folks online. So is this just the materials of the solar panel, or is this like what people actually pay when they install them? And it's the second one. So this is the all-in installed cost for solar. And you can actually see, yeah, it's sort of broken out into different components here, exactly. So you've got the hardware would be module and inverter, and the other hardware, nuts and bolts and things like that. And then this is labor, and then this is other things, getting permits, recruiting customers, the profit of the installer, all that kind of stuff. And so you can see that the hardware cost, the black component in particular, the module cost, has gone down a ton in this time frame, but the soft cost, the orange component, has stayed not constant, but it hasn't reduced by the same amount, basically. Yeah, that's a very good point. So the subplots here are basically different solar applications. So this is rooftop in the top row, and this is residential, so housing units, versus commercial office buildings and things of that nature. And so you can see that for commercial, the arrays typically tend to be cheaper per unit of generating capacity than they typically are in residential. And part of the reason there is just that, if you're a Walmart and you want to get a bunch of solar on the roof, you're going to get a really big array. If you are just one homeowner, you're going to get a much smaller array. But a lot of the work that has to be done to install a solar array is roughly independent of the size of the array. The permits you need to pull, the trucks you need to roll, all that kind of stuff. It really is going to be the same whether you're doing a small job or a big job. So those things tend to kind of wash out a little bit more in the commercial setting where you're doing larger arrays, so sort of 100 kilowatt scale arrays. And then this is utility scale. So this is kind of an order of magnitude bigger than even what you would find on say, a big office building. So if you drive from Lafayette to the Indianapolis airport, I think as you get close to the airport, you pass a big solar farm. So it's not huge, but it's pretty big. So that would be kind of in the utility scale PV sector. And so here we again see a cost decrease from about $1.70 per watt, kind of in 2020 in the commercial, down to about $1 per watt at the utility scale. And then this is for a fixed panel, basically something that you bolt in place and it never moves throughout its lifetime. You send someone out to maintain it periodically, but the panel itself is not moving during the day. And then this is with what's called one or single axis tracking. So here you might have a motor, or it might be a passive system that basically adjusts the positioning of the solar panel during the day to kind of track where the sun is in the sky. And so you can see that single axis tracking is only slightly more expensive today than a fixed axis. So we'll talk a little bit about, again, how, if you could do this, if you could orient the panel, how you might do that, and what angles you might choose at different times. Solar is one DER that's of interest for us. Another is batteries. And here I'm plotting a similar graph. This is from 2013 to 2023, so slightly different time frame. But again, we're seeing basically the normalized cost of a battery system on the y-axis. And here it's normalized per kilowatt hour, which is a unit of energy. In class on Thursday, we'll talk a little bit more about the various units of energy. But basically, if you have a 1,000-watt light bulb and it runs for 1 hour, it would use 1 kilowatt hour of electricity. Anyway, so this is basically how big the battery is this kilowatt hour thing. So you can see, again, a similar trend where 10 years ago, the cost was at $780, or about $800 per kilowatt hour. And today it's around 140, which is roughly an 80% reduction in cost. And this is why we've seen an explosion in all sorts of battery-powered stuff, right? So this is why we see people riding scooters and e-skateboards and e-bikes and all sorts of e-mobility around town. Basically, the cost reductions have made devices like that affordable. We'll also talk about electric vehicles in this class, which from our perspective, the modeling perspective, are basically just batteries on wheels. So here I'm showing a 1-day time span from 3 in the afternoon one day to 3 in the afternoon the next day. And on the y-axis here is the electrical demand from a neighborhood. This is about, I think, 35 houses, and they're in Western New York. And the black curve here is the baseline, kind of what we use today if we don't have electric vehicles. And then the red scatter here basically is a distribution of electricity demand from the electric vehicle charging that kind of lands on top of that base load. So you can see here the base load from the community peaked at maybe 120, but on a really extreme day when everybody is charging their electric vehicles at the same time, we might be up here at 160 or 170 kilowatts. So that's a pretty significant increase in peak demand from people basically, instead of going to gas stations to gas up their internal combustion engines, they plug in their vehicles in their own homes. And we'll talk about electric vehicle charging. We'll talk about how it's done today. We'll talk a little bit about how it could be done potentially better. Another big thing that we'll talk about in this class is heating, ventilation, and cooling systems. So who knows what a heat pump is? Some people took my undergraduate thermodynamics class where we talked about these a lot. A heat pump is basically, you can think of it as just an air conditioner that runs in reverse. So an air conditioner uses electricity to move heat from a cool place, like the inside of an air-conditioned building, into a hotter place, like the hot outdoor air in the middle of summer. And a heat pump basically can do that, but also can do the opposite, which is during winter, it might absorb heat from the cooler region, which might be the outdoor air or the ground if it's a geothermal heat pump, and then use electricity to basically move that heat inside, kind of against the natural direction of heat flow in order to keep the indoor of a house or tank of water, something like that, warm. So heat pumps, something that I work on a fair amount in my research. Our TA, Nada, has joined us as well. It's something that she thinks a lot about in her research as well. So why do we care about heat pumps? Well, basically to decarbonize. If we care about decarbonization, some do, some don't. We'll talk a little bit about that as well. But heat pumps can play a central role in that effort. Today, especially in northern climates in the US, a lot of us heat by burning some sort of fossil fuel, propane, heating oil, very often natural gas. If you can use clean electricity in order to provide heating with something like an efficient heat pump, then you can both reduce emissions from heating buildings, but also potentially reduce costs and air pollution and some other metrics of interest. We'll also talk about heat storage or thermal storage, which can take a few different forms. This is a very simple type of thermal storage, which I guess people would call something like a box of rocks. These are basically bricks. Particular bricks chosen with materials that have good capacity for storing heat, but basically just bricks. And then these U-shaped things here are electric resistance heating elements. So you run current through them and they get hot, basically. So you take electricity into this device here, you heat up the bricks. And then if you want to use that electricity later, say when your heating demand is higher, or maybe your electricity price is higher at some times, lower at other times. You might use that stored heat basically by, there's a blower or a fan in here. It just takes cool air from the room, blows it over those hot rocks, and then vents it back out to heat a room. This is a modular unit. I think the dimensions here are probably something like 4 or 5 feet in this dimension, and a foot or 2 here, and maybe 3 or 4 feet here. And you could get one of these. These are common sort of in certain places. And Montreal, Canada, for whatever reason, they have a lot of these. Some places in the UK, and you can find isolated kind of pockets, like in Western Pennsylvania, for whatever reason, a bunch of apartment buildings that were built in the 70s and 80s have these units in them. Another way to store heat is in water tanks. So this is a domestic water heater, and one that uses heat pump technology. So here, there's a heat pump basically that sits up top here, and the bottom 3/4 of this is just an insulated tank of water. And this unit basically pulls energy, thermal energy from the ambient air, and injects it into the water in order to keep water hot so people can wash dishes and take showers and things like that. So we'll talk about how to model these things, and in particular, why they might be interesting and useful for doing things like reducing emissions, saving money, and so forth. Okay, so I've hinted at some of these themes, but why might we be interested in studying DERs? So I think climate is one major motivation here. So climate scientists tell us that basically we need to reduce greenhouse gas emissions from human activities quickly and significantly. And DERs can play a prominent role in that. Maybe you don't care so much about the climate motivations. Maybe you're just interested in getting a good job in an exciting technical field. Well, DER adoption is already taking off. I'll talk about some trends here in a moment, but things like electric vehicle sales, installations of solar panels, adoption of heat pumps, and things like that are accelerating rapidly. And so there's a lot of growth in that. And I think when you're thinking about what field to work in, trying to skate where the puck is going and plan ahead a little bit makes some good sense. And then why do we need to apply kind of engineering know-how to DER systems? Well, we can improve the user experience of DERs. So maybe a better control for a heat pump might make people feel more comfortable in their homes. Also, we want to make sure that people, if they have electric vehicles, have enough energy in their batteries to be able to go where they want to go when they want to get there. So it can make things like travel times more convenient and so forth. Also, we can deepen emission reduction. So if we can improve the efficiency of how devices are operated, they need less energy, use less carbon dioxide in the production of that energy. Maybe we can make things more affordable for people. We can come up with better designs or better operating principles that save people money either upfront or over time on energy bills. And then it turns out that DERs can play really interesting and crucial roles in maintaining reliability of the electric power grid. And of course, we know that electricity plays a crucial role in many of our lives, and from the consumer electronics that entertain us to the medical devices that keep some folks alive. So DERs often can provide electricity even during power outages and potentially provide life-saving services. But even during non-emergency conditions, coordinating the operation of DERs can basically make the operation of the power grid more reliable and more efficient, and save a lot of money kind of at social scales. So those are the big themes, and I will go into a little bit each of them with a little bit more detail here. So when I started working on climate, I guess 15, almost 20 years ago at this point, we used to use the future tense a lot. Like in coming decades, the climate will change. And now we just can use the present tense, right? So we already are seeing impacts of climate change kind of across various geographies and various sectors of the economy. This is a graph that is made by the National Oceanic and Atmospheric Association, NOAA. And on the y-axis here, the left-hand y-axis, we have the number of events, basically natural disasters that cost at least $1 billion. And this is adjusted for inflation, kind of inflation. So this is in today's dollars. And on the right-hand axis, we have the cost of those disasters. And these are broken out into various things: droughts and wildfires, floods, severe winter storms, freezes, et cetera. Tropical cyclones, this is basically hurricanes. So we can see the rates of these things, the number of them per year is increasing over time. The span here runs from 1980 through 2024. So we're seeing more of them, and we're also seeing basically higher cost of these things. So the severity is also increasing. The group at NOAA who makes this graph and keeps track of this data was located, I guess maybe will be located again in Asheville, North Carolina. And actually, in a kind of cruel twist of fate, Hurricane Helene, when it came through the southeast, actually obliterated the headquarters of the people who make this graph. So $1 billion disaster basically wiped out the scientists. They're fine, right? But the headquarters of the scientists who keep track of the $1 billion disasters. I just note that wildfires also are among the things that are basically become more frequent and more severe in a changed climate. So the tragic fires that we're seeing in LA currently, it's hard to say exactly, that they wouldn't have happened if people hadn't changed the climate as much as we did, but certainly the odds of things like that happening are higher in a changed climate. The reason for that, just not to go into too much detail, but basically in California and Southern California in particular, climate scientists tell us that basically climate change has kind of heightened the extremes of precipitation. So we see both more rainfall in some years, really severe rainy years, but also really, really dry years. And that combination means that there's a lot of growth. Basically, the amount of foliage plants that grow is proportional in some way to the amount of rain that they get. So in some years, you see a lot of growth. And then you have super dry drought years where there's a lot of death. And you also have dried out matter, basically, that lays around, branches, leaves, stuff like that. And so when a small fire starts, the odds that it catches, spreads, accelerates are higher when you have more of that stuff around. Okay, so climate scientists tell us that basically we need to act quickly in order to avoid catastrophic climate change. So there's an international body of policymakers and scientists called the Intergovernmental Panel on Climate Change, the IPCC, which is a UN-sanctioned body. And basically that international organization, almost 10 years ago at this point, made an agreement called the Paris Agreement. So who's heard of the Paris Agreement before? Yeah, almost everybody. I don't need to belabor the point, but the basic idea is that it set targets, voluntary targets that different countries should try to make in order to keep basically global warming below either 1.5 or 2 degrees Celsius. And so this is what's needed from an organization called the International Energy Agency, fairly conservative economic and engineering group. And they say that basically to be on track for those climate targets, we need to, especially in developed countries, reduce emissions by 80% from the 2022 level by 2035. And 60% in developing countries, basically. And the rationale there is that developed countries typically have emitted a lot more carbon dioxide and other greenhouse gases historically. We also have more capability to act. So the idea is that we should do a little bit more in developed countries like the US than folks do in developing countries in order to make room for things like people coming out of poverty in Southwest Asia and so forth. Yes?
Do you know if in 2024 are we above or below 2022? Like,
I'll show
Okay,
some graphs of this. The question for folks online was, do we know how we're doing relative to the 2022 level? So here is overall US greenhouse gas emissions. So this is running from 1990 to 2035. With the black data is historical data, and the blue is kind of what is needed to meet this IEA projection, basically. And on the y-axis here is total greenhouse gas emissions. So this is gross. There are also things that absorb greenhouse gases. So the gross minus that absorption would be the net. I'm not plotting the net here. I'm just plotting the overall emissions. And so you can see over time from 1990 to 2005, emissions were rising. And then we've seen kind of a modest declining trend in the US over the last roughly 20 years. And there's some noise in this. This drop here basically was due to COVID, reduced travel, air travel, things like that. And then, yeah, I don't know, I guess we're still kind of on a roughly downward trend, but I think the reduction in the US between this year and 2024 and 23 was like a fraction of 1%. So roughly constant emissions. All right, so basically, if you look at the slope of kind of the last trend here from 2005, the last 20 years, versus the slope of this thing, it's about a 5x increase in terms of the rate of emission reduction that is needed. And then I'll break this out, basically same graph, but different scale on the y-axis. So breaking out kind of the components that make up this overall US trend. So this is industry, things like manufacturing, plastics, fossil fuel, refining, concrete, steel, et cetera. So this is kind of modestly decreasing, driven in part by efficiency improvements in industrial sector, but also driven by offshoring, basically taking heavy manufacturing out of the US and moving it overseas. So here, the ratio of slopes is about a factor of 13. So a lot of speed up needed there. This is the agricultural sector. So you can see that agricultural emissions are actually rising in the US. So we need to not only turn that trend around, but also speed it up pretty significantly. This is the transportation sector, which I believe is currently the largest sector in US emissions. You can see the notch here from 2020 due to COVID shutdowns. And yeah, the trend here, we need about a 14x speed up compared to what we've been doing. This is the building sector, and so things like the places we live and work. One thing to note is that this is what are called direct emissions from buildings. So this includes like basically burning fuel to do stuff like heat space, heat water, cook food. It does not include electricity use. I'll show the electricity sector in a minute, but basically we assign the emissions from the lighting and the power and stuff that we use here to the electricity sector and keep track of those separately. Anyway, so you can see that basically no trend, pretty much constant, with maybe a mild increase in recent years in the building sector. So again, we need to kind of turn that around and then speed it up pretty radically. So that's all not great news or kind of bland news. The really good news of decarbonization in the US, kind of in my lifetime, has been in the electricity sector. And so here you can see that there's a peak around 2005, and then there's been a pretty consistent decline at not quite the rate that we would need to be on track for these kind of IEA goals, but pretty close. So we need about a 60% speed up in terms of reducing emissions from the electricity grid. So does anybody have an idea of what happened kind of in this 2005-ish timeframe in order to cause these emissions to start dropping? Yes?
It stopped using coal as much.
People stopped using coal as much. Yep. And what replaced coal for electricity generation? Yeah.
Especially solar panels, wind farms.
Solar panels, wind farms, fracking, natural gas. Yeah. So I'll show some graphs of this in a sec. Solar did not play much of a role in this. Wind did, but the most significant role here in the US was primarily from what's called hydrofracking, combination of horizontal drilling through tight, basically rocks, shale fields and things like that, and what's called hydraulic fracturing. So using really high pressure fluids to basically crack rock and bring oil and gas out of them. So that technology innovation was kind of in the early 2000s. And it really took off like wildfire around 2005. And we saw a lot more low cost natural gas on US markets. And people built power plants and used it to generate electricity, basically. Yes.
So this rate that we're at, if we just keep replacing coal with fracking, will we kind of get to where we need to be, or do we need to start replacing fracking with more efficient methods?
It's a wonderful question. So the question for folks online is, if we just kept doing that, if we kept taking natural gas power plants and replacing coal power plants, would we get all the way down to kind of this, where we need to be, basically? And the answer is no. So if we did only that, and we didn't, change how much electricity we use and things like that, we didn't add, more renewables or nuclear than we already have, this thing would kind of look like an exponential decay curve. It would plateau. And the reason there is that, if you look at sort of just the carbon dioxide emissions from burning fuel per unit of heat that you get out, it's about half for gas versus for coal. So you reduce emissions a lot, but there's still a lot of carbon dioxide emitted from burning methane. So that's why we would get kind of a plateau. So we need to do something more than that. And there are many options of what that could look like. And I'll talk about some of them in a sec. So yeah, this is basically an illustration of what we could do. One pathway that we could take in order to get kind of on track with the emissions trajectory that scientists say that we need to be on. So this is a plot broken out by economic sector: transportation, electricity, industry, buildings, and agriculture. The 5 that I just showed in the last 5 slides. And on the y-axis, we again have greenhouse gas emissions per year in units of million tons of carbon dioxide. So the first step in this strategy basically is to kind of continue and accelerate the progress that we've already been making in the electricity sector and bring those emissions down to 0. And this could be done in a variety of ways. So using wind, using solar, using nuclear, basically close to a zero emission fuel, using hydropower, again, basically carbon-free, no combustion involved in that. Geothermal electricity generation, basically using deep hot rocks to heat up a working fluid and then turn a turbine. But also potentially using something like natural gas with carbon capture. So the idea there is to catch all the CO2 that's emitted, put it into a big pipeline, and eventually move it underground for permanent sequestration. I think there was a question or a comment online. If you could just unmute and speak up, that would be perfect.
Yeah, Professor. So I just wanted to know whether the previous trend that you showed, does it also include the possibility of carbon capture? Any case?
Yeah. So I think that like this picture here, going from lots of emissions from electricity to none, we don't exactly know how to do that yet. I think we know how to do about 80% of that. The last 20% is quite challenging. And the question for those in the room who may not have heard was basically, can carbon capture play a role in decarbonization there? And I think yes. I think the US is kind of planning on that to some degree. I think probably it doesn't make sense economically for it to be, the main portion of emission reductions, but a little bit of fossil fuel combustion with carbon dioxide capture, I think makes sense in some scenarios. So yeah, this is certainly something that's on the table. Does
Okay.
that address your question?
Thank you.
Yeah, and thank you. And other folks who are online, please feel free to speak up. Okay, so that's step one, is basically clean up the grid. And then step two, I guess I'll show it in two stages here, is to use all that clean electricity to piggyback on the success that we've had in the electricity sector in order to clean up other sectors. And so here I'm showing the transition from basically all private vehicles. So, cars, SUVs, pickup trucks, things like that, from internal combustion engines, gasoline, diesel, over to electricity. So that would knock out about, I think the grid is about 25% reduction. Private vehicles are about another 16%, bringing the total to around 41%. And then here I'm showing basically things we can electrify using heat pumps. So this is things like space heating and water heating in residential and commercial buildings. It's also low temperature process heat for things like cooking, some refining processes in industry, and other kind of chemical processing. And so that, I think it's about another 20%, and it brings the total to around 60%, somewhere between half and 2/3, which is not quite the 80% that we're looking for, but it certainly gets us a significant portion of the way. And there's other stuff that we can do in parallel. So for example, I didn't really talk at all about the food sector. I didn't really talk about agriculture at all, but there's a lot that we know how to do there that we should be doing as well. So anyway, I know that climate can be a scary thing. Sometimes keeps me up at night thinking about what may happen in the coming decades. But also, I hope that this gives an idea that there's some agency. There are clear steps forward that we know that we can be taking, and it's really an issue of the engineering and the economics and getting the policy right and things like that. So there's a lot that we can do. Okay, so just showing some forward-looking trends here. So this is capacity installations over time from 2000 to 2022 for electricity generation. So this is basically how much new generation was built over the years. And so you can see that a lot of natural gas, this is kind of the dark gray here, was built between 2000 and actually it's still being built today. Coal, the black, it basically only exists between about 2006 and about 2013. So very little new coal has been added in the US recently. Wind power is the green, and so you can see it kind of mildly taking off in the early 2000s, but really around 2005, 2008, that same time period that fracking was taking off. We see wind power taking off as well. And then solar is about a decade shifted. And the reason for that is that the cost declines really were a little bit behind in solar, and it wasn't around until around maybe 2010, 2012 that solar became really, really cost effective. But those cost declines have continued for this whole decade, and now solar actually makes up the largest share of new electricity capacity that's being added in the US. And batteries, basically 5 years ago, were not even a thing on the grid, and today they make up something like a fifth of new capacity that's being installed. So anyway, all that to say, those cost reductions, they translate to the business choices that companies make and to the hardware that we install. Okay, in EVs, electric vehicles, sorry, we're also seeing some pretty exciting growth there. Plug-in hybrids, so this is things like, Prius and Chevy Volt, I guess. We see sort of a mild growth there, but it's really the battery electric or the all-electric vehicles, things like Teslas, F-150 Lightnings, things like that. We see really a large uptake starting in maybe 2019 and continuing through today. And then hybrids as well, we see a pretty significant growth rate. On the heating and cooling world, we see that heat pump sales have outpaced the sales of natural gas furnaces. This is in the United States as well. I'm taking kind of a US focus in this class, although a lot of these trends are similar in other countries. So heat pumps are now basically the most popular way to do heating and cooling in a home. Okay, so that's yes, thank you.
The equalized cost per unit of energy between natural gas and electric has shifted yet? Has switched places yet?
Yeah, so the question for folks online is, has the cost of energy basically used for heating between natural gas and electric heat pumps, have we crossed that threshold yet? So for certain things, absolutely yes. So if you heat with electric resistance, it's basically always going to be better to use a heat pump. It's always more efficient. If you use heating oil or propane, these tend to be somewhat less efficient and higher cost fuels. So the cost per unit of heat output is typically significantly higher for those than for heat pumps. The real competition is between natural gas and electric heat pumps. And there it's really location dependent and price dependent. So in some places, gas is expensive and electricity is cheap. In other places, it's the opposite. It also really depends on how efficient the machine is that we're using. So if we're comparing an old gas furnace to a new heat pump, or a high efficiency heat pump, one that's built for good performance in cold weather, then that might tip the scales. But generally speaking, it's kind of a wash. There aren't huge energy savings potential on the heating side versus natural gas today. But we'll talk a little bit more about the economics. There are other considerations that come into play. For example, a heat pump can provide cooling. So if you have an old air conditioner that's really inefficient, even if you're losing a little bit on the heating side, you might still win on the cooling side. Also, you only need to install and maintain one machine rather than one for heating plus one for cooling. Yep, of course, good question. Okay, so it's transitioning from a little bit of kind of motivational and background material into discussing kind of how the class is going to be structured and how it's going to work. Any questions about kind of the content that I talked about so far? Some really good questions, both from in the room and online, so thank you. Okay, so then we will move on to talking a little bit about class structure. Okay, so before I do that, let me just say the work in this class is going to be maybe different from what you're used to, where kind of you get into a routine and then you kind of stay with that routine all semester. You start doing problem sets weekly, and then exams come up, you study, you take them, and so forth. So here it's kind of almost going to be two phases of the class, where in the first phase, we're going to be doing homework problem sets. We're going to be learning technical material in the lectures, and you guys will be building skills around how to model things and stuff like that, how to write code and simulate things. And then in the second half of the semester, we'll transition more to working on a class project. And the project will be about half of the course grade. So first, it's like, you're building muscles, getting into shape, right? And then the second half, you'll be competing or performing or something like that. Anyway, so we're going to spend the first roughly third of the semester talking about modeling and simulating DERs, including most of the devices that I talked about, but also some others. So the mathematical content there really will be differential equations. So we'll start with a review of linear ordinary differential equations. So PDEs, partial differential equations, which involve multiple variables, are not in the scope of this class. So if it's been a while since you've taken ODEs, that's okay. We'll kind of go back and start from the beginning. And the types of ODEs that we're going to be solving are not particularly complicated. So maybe 10% of the material that you learn in an ODE math class we'll actually use in this class. And then we'll introduce what are called linear dynamical systems, which is basically a linear ODE determined by the physics that basically describes how a system evolves over time. So how the temperature in this room changes over time as a function of the boundary conditions, how much sunlight we're getting, what the temperature is outside, stuff like that. But then typically we layer on top of that a second set of equations which describe our observations of the system. So we may not be able to measure the temperature absolutely everywhere in this room. We may only measure it at one point, like at that wall thermostat. So maybe can we make inferences about what's happening elsewhere in the room, given the limited measurements that we have. And then we'll talk about basically the physics and not the full, nonlinear multivariable physics, but kind of simplified representations of the physics of batteries and EVs, which we model basically as just batteries with wheels. Buildings, so in particular, the thermal dynamics of buildings, how the temperature changes inside of buildings. We'll talk about heat pumps and air conditioners, how we model those. Thermal storage and water heaters, and then solar photovoltaics. So this really is about learning how to map weather data, what's happening kind of with the clouds and temperature into electricity data, how much power a panel or an array would produce. Okay, so that's kind of material that everybody should be pretty familiar with, I think, from undergraduate ODE class. Applied to some systems that you may or may not have studied before, but I think this stuff will be not super challenging or particularly new for many of you. Then we will talk about optimization. And here again, like in a calculus class, you probably learned about how to maximize or minimize a function, take the derivative, set it equal to 0, do the second derivative test, stuff like that. And that's kind of the 1800s version of optimization that we do by hand. Here we're going to be talking more about kind of computer optimization, so how we formulate problems and in such a way that we can pass them to a computer solver to give us a numerical solution to the problem. So in particular, we will talk about a special kind of optimization that's, I think, pretty well suited to DER problems, and this is called convex optimization. And so convex is a geometric term. It basically just means upward curvature, so like bowl-shaped. So you imagine if you're trying to find the minimum of a bowl-shaped function, it's fairly simple. There's kind of just one direction to go in, which is down, as opposed to some kind of weird wiggly thing where sometimes you might want to go down, other times you might want to go up, and the algorithms get a little bit more complicated. So roughly speaking, and we'll talk in much more detail about this through the semester, but roughly speaking, convex optimization problems are those problems that we can pass to a computer and solve globally, meaning getting a guaranteed optimal solution, the best that you can do, and have some guarantees about the runtime of the algorithm. So it won't take a million years, it'll take some reasonable amount of time. And then we will talk about optimization applications to various DER problems, including design. So things like sizing of equipment. How big should a battery be for an electric vehicle? How big should a solar array be for a home? Things of that nature. Also to operation. So if you have some control over a smart thermostat or over when an EV charges or how fast it charges, how do you basically decide how to make those choices? And then we'll talk as well about model fitting. The idea here is that in the previous section, talking about modeling, the differential equations that we'll talk about that kind of govern how these different DERs evolve over time, they all have parameters in them. Something like the efficiency of charging a battery, or the insulation level in a wall that determines heat flow between the inside and the outside. And those parameters we never really know exactly. And oftentimes it makes more sense, rather than trying to sort of look at the materials that make up the wall and pull up tables of thermal properties and stuff like that. Sometimes it makes more sense to look at data, operational data from a DER building, a battery, and then to infer from data what the parameters of those models should be. And so we can use optimization to solve those types of problems. We'll talk about control. It's actually closely related to optimization, but you can think of control, at least in the sense that we'll talk about it, as just kind of sequential optimization. So rather than making one decision, how big should a building or maybe a heat pump be, and then just sticking with it for a long time, you're able to make recurring decisions and periodically get new information. So make a measurement, make a decision, act for a little while, and then repeat. So we'll talk about that. We'll talk about one algorithm for doing that. It's not the best algorithm in the world, but it is usually quite good and applies to a wide range of systems, particularly in the DER world, called model predictive control. We may talk about this or may not, but there are ways to basically do control that don't involve detailed information about kind of the parameters and the structure of a system model. So ways to do kind of more purely data-driven approaches to this decision-making. And then we may talk about some other things. Has anyone taken a class on machine learning? Okay, 1, 2 people. for people, I guess. And how about reinforcement learning more specifically? Yeah, it's usually like a second or a third year graduate class, so I'm not surprised that not many people have taken it. So we may or may not get into a little bit of that, not at a super deep level, but a bit perhaps. And then this problem co-design is really about, like, suppose you want to simultaneously decide how big a battery should be and also how you should charge and discharge it. Should you just always charge it during the day and discharge it overnight, or should you use a price-based charging algorithm or something else? And so co-design is really the problem of how to make those choices simultaneously, rather than first deciding the size and then later deciding how to operate. And we may do some other things. We'll apply various tools here, probably not the full list, but we'll apply some of them to various DER problems, like reducing the cost that people pay on their utility bills, reducing pollution, or providing services to the power grid, things like stabilizing voltages or the frequency of an alternating current grid. And then I would like to do a little bit of machine learning in this class, probably not super duper deep again, but just enough to be dangerous. And actually, that's kind of a theme of the class, is that we won't get super duper deep into any kind of one methodology or one technology, but I want to give you kind of enough to be dangerous. And then if you get really excited about something, I hope that you'll have the kind of conceptual and mathematical framework to be able to then teach yourself more about it, or find the right class to take or the right YouTube videos to watch in order to kind of teach yourself and learn as you go. So we'll talk a little bit about machine learning, and this is all kind of just random vocabulary here, but we'll talk about models that we use to make predictions based on data, how to structure those models, how to validate their performance and things like that. And I think the main DER applications that I'd like to, it's probably will just be like 2 lectures, but that I'd like to focus on. One will be time series forecasting. So suppose that you have, say, some historical data for how much power a solar array has generated over time, and you have some imperfect forecasts of, in the future weather. But the weather forecasts are often wrong. Your app says it's going to be sunny and clear, and then you get rain down in the afternoon, right? So not perfect predictions. How could you combine that historical data and those imperfect predictions in order to get quite accurate predictions of how much power your solar array might produce? You might want to know that so that you know maybe how much money you would make if you're an electricity generation company from selling that power to the grid, for example. And then the second problem here, system identification, really is about, again, using data to find what parameters we should use in our model representation of systems. So what should you use for the insulation in the wall? What should you use for the efficiency of a battery? Things like that. Okay, let me pause there. Any questions kind of about the trajectory that we have planned here? Yes.
What exactly does the project entail?
What does the project entail? Let me put a pin in that. I have a couple of slides on it, and we'll talk about it in more detail. But yeah, it's basically half of the grade, so it's kind of a big deal. The short answer is the project entails what you want it to entail. So you choose the topic. The deliverables basically will be a presentation at the end of the semester and a short, maybe roughly 6-page project report, where you talk about what you did, what was cool about it, how it's unique or different from what other people have done previously. But yeah, we'll talk about more in a sec. Okay, so what are the prereqs for this class? What do I expect you guys to already know? So I think you should have taken a ordinary differential equations class. And again, it's okay if that's 3 years or more in the past for you guys. We will go over how we use ODEs for modeling and how we solve them. You should know a little bit of linear algebra. So this is basically working with matrices and vectors. The math department approach to linear algebra has a lot of span and basis and orthogonalization and stuff like that in it. That's not really what we need. We need kind of more computational linear algebra. It turns out that when you're using computers to solve engineering problems, about 90% of what we do ends up being working with matrices and vectors. So linear algebra in a computational sense is extremely useful for that. We won't be doing a lot of hardcore linear algebra stuff, but we will store data in vector or matrix formats and do some operations on those things in our programming. So you should at least be familiar with that. We will also, again, give some refreshers on these things. And then there will be programming in the class as well. So ideally, in the future, I would love to support kind of whatever programming language you guys are most familiar with, and in particular, different students can program in different languages. We're not quite there yet in terms of having all the course materials, the homework assignments, and things like that set up to support all the different languages that you might want to use. Last year, we only supported MATLAB, so we forced everybody to use MATLAB, even if you'd never used it before. This semester, our goal is we will definitely support MATLAB, and then our goal is to also support Python. So what that means basically is that when we give you guys sample code or starter code for homework assignments, we would give you both, say, a MATLAB script or function, and also more or less the same code written in Python. And Nada is basically helping with that conversion. I wrote the MATLAB stuff last year, and she's helping convert to Python this year. Yes.
If you had to recommend one or the other as far as application in industry or just bang for your buck and practicing now, what would you recommend?
Yeah, so the question is, which would we recommend in terms of bang for our buck now, but also later applications in industry? Actually, probably not the right person to ask about that, not having a lot of experience working in industry. And I think it varies from one to another. So for example, I know some folks who work in automotive who work exclusively in MATLAB and Simulink. And in particular, when they were interviewing for those jobs, companies were like, we really need you to have this particular skill set. And they had a portfolio of code that they could show, right, from projects they'd done, and that was really helpful. Conversely, if you want to go to work at a tech company, Google or Meta or NVIDIA or Amazon or something like that, and you want to work in a more data science type job, I think there the culture is more Python than MATLAB. I think really in terms of functionality, anything you can do in one of these languages, you can do in the other ones. It might take a couple more lines of code or a couple less. MATLAB is really good, basically. So the mat in MATLAB, a lot of people think stands for math, but actually it's matrix. So it's really good at doing kind of fast and efficient linear algebra calculations, which again, that's really the guts of what underlies a lot of algorithms that we use in engineering computing. So it's really good at that. Python, it's made by a private company, right? So you have to buy a MATLAB license, which is sometimes expensive. But the flip side of that is that the company MathWorks that maintains MATLAB develops a bunch of tools and regularly, provides updates and support and things like that. Python is an open language. There's a huge open source community that uses it, but there's not sort of any one company that's responsible for it, which has pros and cons. If you want to share code that you have made, typically Python is more shareable. I actually think Julia, has anybody used Julia before? Has anybody heard of the language Julia before? Get two people. Yeah, so Julia is a newer language, roughly 10 years old, developed at MIT. And the vision is to sort of have syntax that is as clean as MATLAB, but that executes basically as fast as C. So it's a scientific programming language, but it can have orders of magnitude faster runtime than something like MATLAB or Python. Julia is also open source, so if you like the openness, the shareability of Python code, Julia is good there, although not as many people use it. So if you give someone Julia code who's never used Julia before, it's not that helpful. So anyway, that's like a really long-winded answer to a short question without any kind of concrete answer. I think probably my advice for a student who's getting started would be to probably start in Python. I think data science is a huge world. Shareability of code is important. Open source software is cool. There's a lot of support out there for Python. For this particular class, if all you care about is like getting through with a good grade in this class, I think it will be easier for us to support MATLAB than Python because we already have a year under our belt of supporting MATLAB in this class. Anyway, you can make your own decision. I would say our support of MATLAB will probably be better than our support of Python, but we'll do our best to support both. Okay. And then other stuff can be helpful. Again, we're going to be talking about optimization in this class. I will introduce it from the basics, and we won't go super duper deep. But if you've already taken a class in that can be helpful. We'll talk about control. We'll talk about some machine learning and probability and statistics as well. So these are not needed. Again, I won't assume that you have knowledge in any of these, but if you've taken some, it might enhance your appreciation of the class a bit. I also just think most of these things are just good things for engineers to take because increasingly, data and machine learning are important parts of kind of all the work that we do in the engineering and really scientific worlds. And so having some basic skills in these areas, I think is very useful. Okay, homework will be roughly, so I may change the percentages here a little bit and the numbers of problem sets and stuff like that, but roughly 20% of the grade. And we'll probably have somewhere between 6 and 8 over the semester. And they won't be crazy long, but they'll be designed to kind of walk you through some of the concepts that we do in the lectures. And these problem sets will be front loaded in the semester. So I will try to make more room for you guys to work on the projects kind of after spring break. And we'll have more of the homework before spring break, basically. The homework you can do on your own, you can do in a team. Team can be any size, I don't much care. But I do ask that everybody submits their own write-up. So even if you work with 3 friends and you all have the same answers to everything, everybody should write it up individually. And then I think it's okay if you use outside resources. So in the real world, when you're writing code and you get stuck, you don't just like fail the coding assignment. Like you go to a web browser and you search on Stack Exchange or something like that for other people's solutions to that problem. And then you use it in your own code. So certainly in homeworks, that's perfectly fine. If you want to use AI tools, ChatGPT, Claude, whatever, to help you with programming, that's okay with me as well. All I ask is that if you do use outside stuff, so if you pull, some code from an AI tool or from a website, something like that, just write down in your solution where you got it. Say, I'm borrowing some open source code that was published on Stack Overflow or whatever. And then, yeah, to really learn from the homework, like there are a million outside tools. You can sit with your smartest friend and just kind of copy what they do. There's a million ways to get help with homework. But I think the real value of homework is not getting, the 20% of the grade. Honestly, like 10 years from now, no one will remember what grade you got in this class. You probably won't either. But the lessons that you learn, I think can last a long time. And so if you really want to get those lessons, I think just trying the homework on your own without any outside help, other than conversations with friends, I think is the best approach. Basically, the idea is that you identify what you don't understand, right? So first you have to get things wrong in order to understand what you need to relearn. Right? Okay, yeah, homework front loaded in the first half and then second half more focused on the project. My plan is to give a midterm exam. I should say this was also my plan last spring. And I got behind on creating the lectures and I just never made an exam. And so last year, I think we made the homework like 40% and the project 60, and we just didn't take an exam. So that may happen again this semester. It also may not. I will do my best to create an exam. And it probably will be maybe the week or 2 weeks before spring break. And again, because this is a hybrid class, there are about half the classes in person and half is online. I don't really want to do kind of a timed in-class exam, just because proctoring that with online students, I think would be really annoying for them and for me. So I think we'll do a take-home exam. And the basic format of it, is going to be, well, I don't know, but my goal is to give you basically a problem that more or less pulls from stuff that you've already done in the homework. So really, I just want this to be a check that, you've been keeping up with the homeworks, you've been checking the solutions, correcting things that you might have gotten wrong, so that you'll have, code bases. You'll have a few functions that represent, how to simulate a electric vehicle or how to control a heat pump, something like that. So that if I, combine a couple of DERs and do an exam problem and give it to you guys, you can more or less pull up code you've already written from homeworks, adapt it a little bit, plug different functions in together, and then have a solution. Right, so it shouldn't be too challenging if you've already been keeping up with homework. No final exam. We'll have a semester project, again, roughly half of the grade. This you can do individually if you want to. If you're the kind of person who prefers to work alone, that's okay. I'm not going to tell you no, but I do encourage you to work in teams. So we have roughly 50 students in the class. And so I don't know if we had teams of 3 or 4, that would be perfectly fine. That would give us roughly a dozen teams, something like that. We will provide support in forming teams. So if you don't know anybody in this class, I think that's okay. We'll plug you in with other people who have similar interests. Yes.
Do you think the grading or evaluation process would change depending on if you do alone versus if you did it in a team?
Yeah, I mean, so the question is, would the grading change the expectations depending on if you work alone versus in a team? Yes, I would say mildly. So if there's a team of 4 versus a team of 1, I don't expect 4 times the volume or quantity of work or quality of work from the team of 4. It might be like a factor of 2 or something like that. But yeah, if you work alone, I probably won't expect quite as much from you, as opposed to if you have a big team. If you want to go over 4, I think just talk to me. We can figure it out. A team of 5 or something might be okay as well. But yeah, I will take into account team size to a degree when grading. Okay, so what will the project entail? I will give you, like in each homework set assignment, I'll probably give you something about your team. So write down your team members, write down roughly the topic that you guys are thinking about for your project, stuff like that. We will have a few larger deliverables along the way. So toward the middle of the semester, we will have pitch presentations. So you will have formed your teams, you will have talked about what you're excited about, picked some topics, and then have some ideas of what you want to do for the project. And then we'll have like a mini conference in class. We'll probably spend 2 classes on this. And I will ask the online students to join those in real time. And we'll give presentations. Basically, one student will stand up from your team and talk for maybe 5 or 6 minutes about what you envision, what other people may have done in the area, and why what you're doing is cool or different. And then your classmates can ask questions, try to clarify. I also may ask some clarifying questions. But the idea is more or less just to like force you guys to put in the legwork so that you can stand up in front of your friends and not be embarrassed when you talk about what you want to do for the class project. And then toward the end, I think we'll have probably the last 4 classes of the semester probably will be, again, this kind of mini conference format where same deal, each team will nominate 1 speaker. And you'll give a somewhat longer talk, maybe 10 to 15 minutes, somewhere in that range. And then we'll do a few minutes of questions afterwards. So this one will not factor hugely into the grade. It's more like, did you do it, right? But this one, the quality of the talk and what you did will factor into the project grade. And then we'll write a final report. And oftentimes, like, I don't know, when you're taking your humanities requirement in your freshman year or something like that, and you have a paper assignment, they'll say it must be at least 8 pages, right? But I actually say this project can be at most 6 pages. So I do not want you to write a long and rambling report. I want you to write a tight report that captures concisely the stuff that you did. And for grad students, like, we'll probably style these things in about the same way that you would style a conference talk or a conference paper. And I'll give you templates and formats for this stuff as we get closer to the due dates. And then I added this piece here. So I'm sure everybody who's done a team project in class before has had the experience where, you know, maybe 1 or 2 people on the team are really excited about the topic and work super hard. And then a couple of other people are less interested or more busy or whatever. And the workload, the share of work between the team can feel unfair at times, or anyway, at least disproportionate. So what I want to do to try to counteract that to a degree is I will have a meeting with each team at the end of the semester, either in person or on Zoom. And then I will just ask each person on the team to self-assess their own contributions to the project. And you'll say it out loud in front of me, in front of our TA, and in front of your teammates. Okay. So I won't ask you to grade each other, but I will ask you to just honestly self-assess your contribution. And I don't think it's evil or wrong if you say I contributed less than average to the project, right? People have busy semesters. You know, some grad students have other, you know, talks and things like that they have to do during the semester. I think it's okay. I just want to be honest, and I'll probably just adjust your project grade by like 1 level. So if the class, the overall grade is an A, and you say, yeah, it was a really busy semester for me, you know, I just couldn't hack it. I didn't do as much as I wanted to this semester, I might drop it down to an A-, something like that. So it's not going to be a huge correction. It's more just to sort of keep each other honest, if that makes sense. Anyway, so any thoughts on that? Any horrible objections to that idea? Okay. All right, so we're low on time, so I'll wrap up here. There's basically my website, kevinjkircher.com. You can just Google my last name in Purdue, and this comes up. Click on teaching, and then DERs, and you get all the material for this class, which again, this is where you can find the lecture slides. So if you want to mark up the PDFs on your tablet as we're doing lecture, you can do that. Nada has set up a Slack for us. So if you don't have time to come to office hours, but you want some help on interpreting a homework question or something like that, you can post on Slack. You guys can help each other out there, and also Nada can provide some support there. The syllabus is up here, and I will populate these other things kind of as we go. So I'll put up a lecture video of what we just talked about today, probably this evening, and then we'll post homework and starter code and things like that. And then you can see last year's archive of what we did in this class. So if you want to hear me give a nearly identical lecture to the one that I gave today with minor changes, you can come down here to our YouTube channel, and you can see it's probably going to play an ad. Yeah, Liberty Mutual.
Liberty Mutual customized my car insurance.
Anyway, you can find the lecture videos kind of all up there. These will change over the course of the semester, but probably not more than 10 to 20% per lecture. I'll also add a couple more lectures this semester relative to last. But if you want to work ahead, you're welcome to do that. Okay, so that is one of our websites. And then we'll also use Gradescope, basically for uploading homeworks so that our TA can grade. We also have a Brightspace page that I think everyone was enrolled in. We won't use that very much, but I may put up some materials that just aren't suitable for like, broad, just totally public, like anybody can go to my website. So if there's something that's relevant to the class, but not to other people, we'll put it up there. And then for folks who are participating online, basically you can look over the slides and the videos whenever it works for you. You can also join in time if synchronous is better for you. If you want to be able to ask questions during lecture, you're welcome to do that. Upload the homeworks and the midterm on the same deadline, the same schedule as the rest of the class. Office hours, both Nada and I will hold, and they will be hybrid. So you can either come to my office or Nada's, or you can join on Zoom. And then, yeah, do the project. Again, if you really want, you can work on your own, although I encourage you to work in teams. And that you can do remotely. And I would just suggest that you guys set up, Zoom or Teams or whatever your favorite video chat is of choice, and have periodic meetings to kind of keep everybody involved in the project. And then I will ask you to join in real time for the presentations, for both your own team's presentation, but also to provide comments and questions on the other teams. And then if you don't mind, I would ask you to just take a few minutes and follow this link, or look at the QR code on your phone here, and it would take you to a short survey. It should only take like 5 minutes or less to fill out. It's basically just some information about you. What's your major? What year are you? What time zone are you in? For things like coordinating stuff like that. So I didn't mention this, but we also, I think, will do a few facility tours over the course of the semester. So we have a test house near campus that has a bunch of interesting DERs in it that we will go look at some point. And then the Purdue power plant, it's called the Wade Utility Plant. It's on the south east corner of campus. And I would like to schedule a tour for us to go there. Not exactly DERs, much bigger scale machines, but I think really interesting to see in an energy class. And we may do one more in addition to that. And then we may also have one or more guest lectures over the semester. So you may get tired of my voice and you'll hear from some other expert. And then we may also do 1 or 2 classes that are about sort of reading something and discussing in class. And those we won't videotape and put on YouTube. That would just be weird. But we will have basically Zoom calls or something, and we'll do kind of discussions that involve both the in-person folks and also online students. So I think that is all. If you have any questions, feel free to email me. I will put up a reading assignment, which is just an article that should take 20 minutes-ish to read, and then a podcast interview with one of the authors of the article. And that's just to kind of prepare you. Next lecture, we will talk a little bit about energy systems broadly, electricity more specifically, a little bit of history and policy in the electricity sector, and then kind of the vision of how DERs can plug into the power grid of the future. So that's all for today, and I'll see you guys on Thursday.